Welcome to Walkabout the Galaxy, the four-way astronomy podcast where the science is universal, the opinions are personal, and the bonds are stretchable but unbreakable. We are
Aww.
Strange, Charm, Up, and Top, the astroquarks, also known as Josh Caldwell,
Addie Dove.
Hannah Sargent.
And Jim Cooney.
coming to you from distributed locations near the Walkabout studio at the University of Central Florida. Remember to subscribe to us on all platforms, including YouTube, Facebook, Twitter, and Instagram. Watch us on YouTube, where you can see the unpredictable flickering of the light in my home office. It's mysterious. For our next music video, which I know everyone is very eager to experience, we actually have a video director who knows something about how to make a good video working on
Wow.
it. And the video will feature original artwork from @Reasons My Friends Hate Me. Check it out on Instagram. That will be available later this fall. If you'd like a Walkabout the Galaxy t-shirt, send us a note at wtg@ucf.edu. Our stumper today is touristical, perhaps. Fictional touristical. What alien or fictional land, it can include planets, but it doesn't have to be another planet, would you like to visit for a month or a year? Jim Cooney, you look like you could use a vacation. Where would you go?
Wait, fictional land? Oh,
fictional alien, yeah. Fictional alien, yeah. So you can't say Mars unless it's like the Mars from
Hyperion.
The one of the shoot, what the heck is the movie with the fake with Schwarzenegger, and they did a remake, and the memory
Total Recall?
implanted Total Recall. Gosh.
Wow. Wow.
Sorry. That was
We're
terrible.
off to a start today.
all right.
You can recall that one,
I'm not going to Mars anyway. Mars is stupid no matter what. I'm going to Ryza.
Excellent choice. Ryza from Star Trek: The Next Generation.
Yeah, it's like a vacation world or something like that. Like the whole planet is just like pleasure everywhere in every way, and I'm on board.
Yeah.
Unless the weather sensors get messed up.
Would you be looking for Jamaharon on Ryza?
Yeah.
I don't know. I can't remember what that is.
It's okay. I know nothing about anything Star Trek, so this is just a lot of words that I don't understand.
Yeah. So you don't know if you should get a Horgon or not if you go to Ryza.
I mean, get a Horgon. I don't know. Maybe that's a delicious sandwich or some kind of party thing or something. I don't know. Either way,
I was so happy with your. And it tells, and it demonstrates to everybody that you're ready and interested in Jamaharon.
Exactly.
And you definitely want to get one of those.
Yes.
Take it from me, because I've been there and they're awesome. Hannah, where would you like to go?
I want to go to Pandora.
Ooh.
Oh, the Pandora of Avatar, not the Pandora.
Of the Avatar.
Of the Avatar Pandora.
Yeah.
It was a little bit conflictual. I mean, in our one time that we saw it. You need to pick your time, I guess.
Yeah, that was the other thing. It would be Pandora pre-colonization of
okay.
Of the Earth worlds. I mean, I saw it in IMAX. It was beautiful, and I'd happily just hang out there and enjoy the beauty. That's
Are you excited about the new Avatar movie?
I am, and I don't watch trailers. I don't do any. I just want to go in completely blind and just take it all in. So,
wow.
Yeah.
Okay.
I would go to Avatar, but if we're talking pre-colonization or invasion Avatar or Pandora, I don't think they had like plumbing, which is very important to me.
You're not much of a camper.
I am not much of a camper. Is an understatement.
It's an understatement. Okay.
Yes. I am not of a camper to any extent whatsoever.
But you do like the travel. You do like the travel piddle pockets, Josh. You love those. Just kidding.
Sure. And I have camped, so I know of what I speak. All right, Addie, how about you?
Well, I mean, I think I'm going to go with Wakanda, which is part of the reason for this question, I think. But because like Wakanda looks cool and interesting, and if and it's on Earth.
True. So the travel, getting there to and from, is easier than going to Pandora.
It seems like it's got a really awesome mix of like both technology and nature, and I like that.
Yeah.
Is this Avengers Warfare?
Pre-war, pre-invasion from other dimensions or whatever.
Yeah.
Okay. I'm liking Jim's answer. That's what I'm gonna go to to Ryza also.
All right, man.
Yeah.
I'll see you there, buddy.
Oh, maybe different times. Or same.
We can check in with each other.
That's true.
See how it's going. Together. Yeah. Well, today we'll talk about lunar explorers, a different kind of WWW, and a very old Martian rock, amongst other things. But first, this episode of Walkabout the Galaxy is brought to you by jeans length. Whether you like your jeans bunched up at the cuff, tapered to your ankle, or cut off mid-thigh, for your star formation needs, you'll want to get the original jeans length. Depending only on the temperature and mass density of an interstellar cloud and a few universal constants, calculate the jeans length to determine if your cloud will collapse under its own weight like a pair of acid-washed pants or expand to a new equilibrium like stretchy denims. With options for oscillation wavelengths and cascading fragmentation of giant molecular clouds, check your jeans length for your fashionable Walkabout the Galaxy. Jeans length. Be an outsider.
Oh, be an outsider.
Just because of the theme, I'd have to say Levi's.
I like it.
That's all I've got.
Reasonable.
Ooh, LL Bean. That's a good answer.
I said LL Bean. Yeah.
LL Bean. Addie, what do you think?
Yeah. I was also thinking some sort of clothing company, but I couldn't decide which kind. So maybe I'll go with like along Jim's route and go with like Patagonia.
It is, in fact, LL Bean.
Oh, nice.
Yeah.
Is that an outdoor? Did you say outdoors brand?
It's
they
not entirely, but mostly outdoorsy type clothing.
Okay.
Yeah, for like camping gear, camping clothes, hiking, things like that. Since space news, there was a headline about it, the shortest day ever having been measured recently, about 1.5 milliseconds shorter than the previous record. Usually I think about the day getting longer.
Indeed.
Because over a long period of time, it is getting longer. So what goes on? How does the day get shorter?
We don't really know.
There are some thoughts. I mean, we know in broad strokes, right? I mean, the length of the day is largely, the kind of Earth-Moon system is a fairly isolated system, and so its angular momentum is conserved. This is usually why we think of the day getting longer, right, is because the moon is slowly stealing a little bit of Earth's angular momentum, and so Earth is slowing down. But this is over millions, billions of years type of timescales. But the other way you can kind of change the rate of spin of the Earth is to kind of rearrange the Earth's mass. So it's got to be something along those lines, right? You change the shape of the Earth ever so slightly, and that changes the rate of Earth's spin because that changes the distribution of mass in the Earth. So I thought that the one idea people had was that as the ice caps melt, that changes the distribution of that causes like the ground beneath those ice caps to push up a little bit because there's less weight above them, and that makes the Earth a little bit more spherical and less oblate. And
so it's the figure skater pulling the arms in. Then
it's a skinny Earth.
The Earth is a little bit like a figure skater with the arms out. It's a little bit bloated around the equator. Right.
Is that because how much variation is there in that time of day? Like, is it within the realms of general variation?
this particular record was a 1.5 millisecond variation. So
I
the
don't know
Earth,
what normal variation is.
well, I mean, you know that the period is 24 hours or 23 hours and 56 minutes.
56
so 86,400 seconds, give or take. And so that's 10 to the 5 seconds, and this is 10 to the minus 3 seconds. So it's a 1 in 100 million part.
But that doesn't answer the question
difference.
of like what are normal plus or minuses for a day.
I think they're on that order. This didn't break the record for shortest day by very much, only by a few hundredths of a millisecond or something like that. But
yeah,
it varies. And yeah, I mean, like Eddie was right. I mean, I don't think it varies a lot, and we don't always know what the reasons are. That's just like that was some hypothesis about maybe why.
The sort of moderately long term, not really astronomically long term, but one other piece of information you can have is that leap seconds are added to the official timekeeping record when the measured rotation of the day gets out of sync with the sky. By a second, we add a second, and we never have had to subtract a second. So it is getting longer, and even in our lifetimes, on the order of 1 or 2 dozen leap seconds have been added. So I've had in the Cassini mission, we had during that 13-year mission, there were several leap seconds that were added to the official time clock. Now, that the day isn't actually 10 or 20 seconds longer now than it was when we were born. So there's some funny wiggling going on there, but there are changes that add up to the order of a second over the course of on the order of a year.
Mm-hmm. It looks like the average day variation is like plus or minus less than a millisecond. So it's like somewhere between, so it's like often around a millisecond. So it's 24 hours, basically like plus or minus a millisecond.
I feel that like when my alarm goes off and I've been gypped at a millisecond.
Too early.
I feel that.
Too early.
Yeah.
Hit the snooze button for another 2 or 3 milliseconds. Yeah. But it is interesting because you say the sort of redistribution of matter on the Earth. You mentioned the melting of the ice caps, and you think, oh, well, that changes what's going on up here. But what's going on near the axis of the Earth's rotation isn't really going to affect the spin very much. It's consequences for the overall global shape that could change things. So pretty interesting. Hannah, I think there was a news item that you were particularly excited about that you wanted to share.
I am excited about this news item. So, actually, the image behind me is quite apt. So there's a French researcher.
It's wrong. Because it's also wrong.
Also because it's wrong. Yes.
You might look at pictures of the sun and think that looks like a slice of
pepperoni,
sausage, or cured meats or something like that. So a French researcher shared an image. Purportedly of a James Webb image of a Proxima Centauri, was it our closest star?
Yes.
And then later revealed, because it got a lot of traction, and then later revealed it was actually just a slice of chorizo, which upset a few people and entertained many more. I quite liked it because well, first of all, he said it was a joke, which is like fair enough. It was good, but also kind of highlighting, just because you respect someone doesn't mean that you should still fact check, and you can't just take someone's word on Twitter without, published articles and research and all these other things. And of course, he did admit it. It's not like he just ran with it indefinitely. But I can see that it's, to some people, a bit contentious.
It's the picture is nice because it's like a slice, and it looks like it's maybe backlit. It's glowing. Like I don't know.
Yeah.
I don't know if he took the picture
or he put it on a black background.
If he found it or something. But it looks like there's light coming through it or something. Is it maybe just reflected? Maybe it's just going through.
It's just
through a thin slice and then bouncing back out. It looks sort of glowy. plausibly like an alien star.
I love how when you first look, if someone told you that was a picture of a star, you'd go, wow, that's phenomenal. And then as soon as someone tells you it's a slice of chorizo, you realize, of course, it's a slice of chorizo. It couldn't possibly be anything else.
Yes.
Yeah.
I feel like in one of the tweets when he was explaining it too, he said something about being at a cocktail party, which I also very much appreciated.
Yeah, scientists are humans too.
And Addie, you're in our final space news. There's another mission to the moon.
Yeah, there was exciting. There was an exciting day. Was it last week now? Yes, last week when there were 2 launches from the Cape in one day. There was an early morning.
Both of them by exactly 3 minutes, completely accidentally.
So you saw the trails, but you didn't see the launches.
I was unaware of both of them, and I walked the dog at 6:30 in the morning, and I see this beautiful, fresh contrail from what turned out to be an Atlas V launch, and it had just happened, because I've seen enough of these. I know how long it takes for those things to dissipate. And then roughly 12 and a half hours later, I'm driving in my car, and right in front of me, I see another contrail. And that time the sky was clear enough. I could still spot the rocket just before the main stage shut off. So it was like 3 minutes too late for that one too.
Yeah. So this one,
but that one was the one you're going to talk about.
Yeah, the Atlas V one was good. It was some Earth satellite. I don't know. I think it was a military one.
Yes.
The SpaceX launch, though, was a Falcon 9 launch of a moon orbiter, which you think, wait a second, Addie, I've listened to you talk about space things enough to know that Falcon 9 isn't going to get a big old spacecraft to the moon. That's why we have our bigger rockets that we're launching to be able to get things to the moon, right? Dear listeners, that's what you're saying.
That's exactly what they're saying.
That's what we're saying, Addie.
But this is exciting for a couple of reasons. So this is the Korea Pathfinder Lunar Orbiter, or KPLO, which is a Korean satellite that's intended to study the moon. And one of the reasons it's fun is so it's launching on a Falcon 9, and it has some of its own little rockets, but it doesn't have enough propulsion from that to go directly to the moon. So it's actually doing one of these BLT orbits. We're on a very meat theme today. We're on one of these ballistic lunar trajectory orbits to sort of go and sort of circuitously get to a lunar orbit. And this is South Korea's first lunar mission. It's going to hopefully orbit the moon for about a year, and it has a lot of really cool experiments, including one US-built payload. It has a terrain imager, a polarimetric camera, which I'm really interested in. So it's going to study how the polarized light, looks at different scatters on different areas on the surface. It's got a magnetometer, a gamma ray spectrometer, and a thing called shadow cam that's really high sensitivity and is supposed to look more in shadowy regions.
Oh, nice! So, a low light sensitive camera for the darker. Cool. So
hopefully it'll get into orbit in December.
Okay, that was going to be my question: how long it'll take to get into its orbit. And it'll eventually be in a circular, relatively low altitude orbit, right? Like a 100-kilometer orbit or something like that.
A roughly 100-kilometer polar orbit. And if it gets extended after that, they'll go a little bit lower.
Lower down. Nice.
Yeah. It's hard to orbit the moon, it turns out. It's got really inconsistent gravity.
Right.
So it's actually really hard to have a nice stable orbit around the moon. So you like to start farther up. And you can stabilize, and then you go lower. What?
What does inconsistent gravity mean?
It's lumpy. It's lumpy.
It's lumpy.
Is what it means.
Yeah. So it has these regions called mascons, which are mass concentration is what it's short for, where it's heavier elements basically got concentrated in some of these areas, and that's part of the reason it's the gravity is lumpy.
Yeah. So
it's weird.
To first order, if you're far enough away, it's like a dot. And it's very easy to put yourself on an orbit around a dot, and you can just stay on that orbit forever. But the closer you get in, the more the imperfections matter. And the moon has got a lot of those imperfections frozen in. It's kind of crazy. Yeah, lumpy. So, which is too bad, because it'd be cool if you could put something on an orbit that was just 10 meters higher than the the tallest hill or whatever.
That's what I was thinking.
Yeah.
Screaming overhead because there's no air to slow
There's no
you
air,
down,
right?
right?
So, so yeah, you could do that. I guess you can't though.
But the little weak gravitational perturbations that you would get from the fact that you're getting pulled, you're not you're not orbiting a perfectly spherical object would cause you to crash really fast if you did that. So
Yeah, Lunar
but that's
Reconnaissance
exciting.
Orbiter, which has been orbiting the moon for a long time, has done several different like changes in where it orbits.
They go down for a bit, but then they go back up so they can hang out for a while. Yeah.
And for the extended mission, they have a little bit of a higher orbit.
Well, before we do our trivia, let's talk about, since we're in the solar system, this move out to Mars, another favorite topic of ours and favorite topic of Hannah's.
Yeah, well, sort of. So I was reading up on this topic.
I don't know. I mean, I think it is, because I just did a crossword where it says the clue was moon, Addie, blank, Hannah. It was 4 letters, starts with M. So I put
moon.
Mars.
They're both
Russia. Yeah, let's go moon. 2 moons.
I thought maybe it was moon, but they have a rule: they never give any of the answers in the clues. So
okay.
It has to be Mars.
We're talking Mars, and we're talking Mars meteorite. So I think we've actually talked about this particular meteorite in the past on the podcast. So it's the Black Beauty meteorite. This is
Black Beauty.
Yep. So this is a chunk of rock that has been ejected from Mars and then landed here on Earth. And it's a special kind of meteorite because we think it's the oldest. It contains some of the oldest rocks from Mars. So it's showing some material that has been preserved from basically 4.5 billion years ago, which is when Mars basically formed.
Which is insane. I mean, the fact that we have something like that is insane.
The fact that it's like it was just described as a free sample return mission to like one of the most coolest regions on Mars, basically. And so there's this team of researchers from Australia, and they've been trying to figure out where did this rock come from on Mars. So can they identify the impact crater that caused this rock to be ejected? And it's a super complicated process. So they basically use, I think, some artificial intelligence, also like machine learning type stuff to basically look at all of these different craters, like all over the Martian surface, and they're trying to identify. They're looking at these big impact craters and then all of the little impact craters that end up scattering on top of it. So this is when you have a big impact, you get loads of debris, and some of that will then fall down on top of it, creating lots of little craters within a big crater. And they identified, I think, like 19 potential impact craters, but they needed to find the area that has so that it would have been able to sample material from some of the oldest regions of Mars, which I believe is I want to say, is it Noachian?
Yes.
Is that the right time frame? Yes. There was one particular crater that happened, or large crater that was in one of these regions that could have originally dug up some of this ancient material. And then there was a second impact that then ejected that
off the surface of Mars.
So there would have been these 2 impacts. You've got these preserved ancient Martian rock, then you've got this newer rock with it, which was around, I think it was about 1.5 billion years ago. And there were certain key features, like certain enrichment in certain elements and certain magnetic properties and things like this, and they were able to kind of find a region that has all of those properties. And I think they've given it a name named after a small town in Australia. They have this interesting naming convention, which is small craters on Mars can only be named after towns that have a population smaller than like 100,000 or something like that. It's a really odd naming convention. But yeah, the fact that they're saying it like conclusively, this is the location of this
So
Special.
it's one of these crazy detective stories. Jim is loving it, I can tell.
I've been shaking my head since the beginning of this. Maybe am I being a doofus for being skeptical that this is even from Mars? How do you like?
Yes.
How do you so conclusively like? I understand things like isotopic ratios and various things like that, but the surface of Mars today is very different than the surface of Mars 4.5 billion years ago. How could you conceivably determine that a rock you have conclusively came from Mars when you're looking at a surface that's so very different? Like, there were other planetesimals that got formed and destroyed in the early solar system and stuff like that. How do we...
Here's my speculative answer, and Hannah or Addie can correct us both if we're wrong here. But my speculative answer is that, remember, this rock was formed on Mars 4.5 billion years ago, but then it's been through some stuff, right? As Hannah was describing, something happened to it 1.5 billion years ago, and then the ejection was only 5 to 10 million years ago, which is basically yesterday. And so the rock, I presume,
I misunderstood.
It has been on Mars until 5 or 10 million years ago.
Okay.
So it can carry isotopic traces of the current Martian environment, and that can identify it as having originated on Mars. Now, this is a serious analysis, and you can read through and see all this stuff. And I've looked at some papers on these radiometric dating, and it really makes my head hurt to think about that stuff.
Yeah.
But so then, piecing together that whole history is pretty amazing.
Yeah, I mean, so you can definitely get the age by they do like zircon dating, I think. I think there are zircons in this meteorite, and they can get like an actual age basically by doing zircon dating. And so it definitely is a really, really, really old. Those parts of it are very, very, very old, right? Like 4.5 or whatever billion years old. The question of whether or not it comes from Mars then, right, Jim, is you do additional chemical and isotopic evidence analysis and show, and we have right, isotope dating, you look at the ratios and where they form in the protoplanetary nebula basically, and where other things on Mars have formed and what their ratios are, and they're different than what we have here on Earth. So
right, but are they different from some planetesimal that formed in an orbit near Mars or something like that?
I think so. I think with everything taken together, yes.
Okay.
So most Martian meteorites, to my understanding, are identified by atmospheric gas isotopic ratios that we see in the Martian atmosphere that are trapped in the meteorite. But I don't know if that's the case here.
I'm also trying to remember. Do you remember? I'm trying to think back to the story that we did on this Black Beauty meteorite in the past, and I think it was to do with the zircon, and that there was, and that zircons can basically capture evidence of giant impacts in their ages. So it makes sense then that this meteorite has gone through sort of two massive impacts before being ejected. So you have the formation impact, and then this zircon has been sort of damaged with
shock
following
processed.
a second, right. and then transported here. So I suppose that almost supports this formation theory as well. So it's a cool story.
I don't actually remember talking about this before, and I don't remember the name Black Beauty, but I really don't. But that doesn't mean anything because I don't have total recall, as we've established earlier in the show.
We definitely talked about some NWA meteorite.
Yeah, that's what I wanted to say.
I think I did the story.
Was that the official designation of the meteorite is NWA 7034, and the NWA stands for Northwest Africa. And we talked about
that.
It's called Northwest Africa because there is no country called Northwest Africa.
Non-specific.
So there's no particular, right. You got to be a little bit non-specific there. Anyway, our trivia today, before we jump out into the realm of physics.
I really want to figure out a way to like work in straight out of Compton or something in one of these discussions too, but I haven't figured out how yet. So I'll hold it.
Okay.
I'll look up
Well,
a better discography and have something to add in.
Well, speaking of discographies, our trivia today is in honor of recently departed singer Olivia Newton-John, who died this week, who was the target of, I was going to say, many teenage crushes when she starred in Grease, but maybe it was just me. I don't know.
I think many.
When I was reading her obituary, discovered that she has a surprising science connection in her family tree.
Okay.
She is the direct descendant of what noted scientist? And I give you multiple choice. Your choices are Carl Schwarzschild, who provided the first exact solution to the Einstein field equations of general relativity; Max Born, who won the Nobel Prize in Physics for, among other things, developing the standard interpretation of the probability density function in quantum mechanics, so psi star psi. He developed the interpretation of what that actually means. William Thomson, also known as the first Baron Kelvin, pioneer in thermodynamics and first to calculate the temperature of absolute zero, also known as 0 Kelvin, now in his honor. Rosalind Franklin, British chemist whose data were used by Watson and Crick to determine the double helix structure of DNA, or James Jeans, who lent his name to this episode's sponsor, the Jeans Link, who, among other studies, included gravitational collapse of clouds of gas to form stars. So those are your choices.
I'm surprised Newton wasn't in there.
Huh.
Maybe you know something I don't know about Olivia Newton-John's
Her name's
family
Olivia
tree.
Newton-John, Josh.
In any event, we'll come back to those choices after our physics topic, which is about some data from the Large Collider.
Large Hadron Collider.
Way to avoid, yeah. That thing just constantly spitting out new and interesting stuff. They, we don't have to build a brand new particle accelerator to get more data. You just keep running it and keep running it and keep running it, and then it helps you improve your statistics for things you're already measuring, et cetera, et cetera. So anyway, as a reminder, the Large Hadron Collider is a big giant thing where they take protons, speed them up to near the speed of light, and then smash them into each other in like a little kid type of thing, but in the most complicated machine ever built on the planet.
Right.
Which is awesome.
It's like, let's break this thing to see what it's made of.
Yeah, it's freaking awesome, right? I mean, that's just the most fundamental thing you can do. Bash things together and see what you come up with. And you, of course, come up with a crazy zoo of different particles, depending on how much energy the protons have when they collide and exactly how, all the details of the collision. You get all kinds of different possible things out of those collisions. And, of course, they're colliding billions and billions and billions of protons. The amount of data that these particle colliders end up with is insane. In fact, that's, of course, the CERN, which is where the Large Hadron Collider is located. This is a big laboratory there in Switzerland, was where the World Wide Web first originated, right? Back in the...
To help deal with some of this stuff,
1980s, right? Yeah, to help these physicists share their data because you couldn't do it with the means they had back in those days. Anyway.
Jim, let me ask you a basic question first to make sure I'm not thinking about this in a very stupid way. But we're colliding protons and antiprotons most of the time, right? Or
I think it's protons
what are we colliding?
You're just
colliding protons and protons, right?
Yeah.
Okay, sorry. Colliding protons and protons with each other, and they're each traveling at very close to the speed of light, so they have a huge amount of energy. Yeah. And when they collide, it's not that like we know what protons are made of. They're made of 3 quarks each, right? I can't remember which 3, but I'm sure you can tell me.
Ups and downs.
So
yep.
it's not like I mean, it's not like, oh, well, let's run those two protons into each other and see what we get. We know that the protons themselves are made of, to whatever that even really means, each three quarks. But we get all these things spewing out because really what we've done in the collision is we've converted all of that to a huge amount of energy in a tiny space. And because energy and matter can be interchanged with each other, from that little pile of energy, particles are formed, are converted from that energy into various different particles. And the more energy you've got in there, the more massive particles can be birthed from that puddle of energy. Is that a correct way of visualizing what happens in these collisions?
Yes, I mean you have to be a little careful because, of course, it does matter what the protons are made of. You can't just make anything out of that soup of energy there because you have to do things like conserve electric charge and various other things,
right,
and spin and various things like this. So it's not just make a lot of. They're not just trying to make the most possible energy and then see what comes out. It's when two down quarks collide with each other, you can make a lot of different things depending on how much energy those down quarks have, et cetera, et cetera. So, I mean,
But you make different things if you had two up quarks or two bottom quarks colliding with each other.
Right.
For
That's
example.
right. You will make different things, but you're right. The more energy they have, the more kind of different paths these collisions can go down. You can make weird random things for short periods of time. Not random, but weird things for short periods of time. So, but it's really amazing to me how good they've gotten at identifying what's coming out of those. Because you're talking about these very short-lived, very high-energy particles that are flying at near the speed of light in every possible direction once you smash these. But they're able to determine what came out of that collision, usually by this ridiculous detective. And of course, I was skeptical of the Mars thing. You should be very skeptical, I think, of these, like how they figure out. Like in the particular thing we're talking about today, we're talking about the production of three very particular particles called W bosons, which are part of the standard model of physics. A W boson is a particle that is the carrier of the weak nuclear force, thus the W.
So this is another term or terminology or phrasing that gets thrown around a lot that I would appreciate your take on. What does it mean that it is the carrier of the weak force?
Right. So
how does a particle carry a force?
Yeah. So this is a different view of physics than you get in like a physics 1 or physics 2 class. And in a physics 2 class, when you're learning about, like, for example, electromagnetism, you talk about the electromagnetic field and you calculate forces based on putting charges into electromagnetic fields. But in particle physics, we don't really think of it of the fields as being like everywhere out there. We think of the force between, say, two electrons as being carried by a force-carrying particle. In this case, the force-carrying particle for electromagnetism is Hannah,
the photon.
Addie, Josh, yeah, the photon, right? So a photon is the force carrying. So it's really like the exchange of a photon between two electrons that tells one electron to push the other electron, right? So this is kind of a different view of how forces work. It's just the exchange of a particle that's telling one thing that the other thing is there. And so that's what, the weak nuclear force, the particle that's telling one particle that the other particle is there are these W, and they're actually the second kind of force-carrying particle for the weak force called the Z boson. So the W and Z bosons tell one particle that the other particle is there. So that's what a force-carrying particle is. And, so those force-carrying particles
has a little knapsack.
What's that?
It has a little knapsack.
Yeah. It has a little knapsack. Goes,
yeah. Hey, that other particle's over there, right?
I've got a message
one of those,
for you.
You're at like a convention. It's like you're at a convention. It's got the little sign. It says like this party's over there. Okay.
But yeah, so that's what a force. So that's what they're making. So this particular article that we're about to be chatting about briefly is just looking at the production of three of these W bosons in one collision. So you take two protons, smash them together. Occasionally, three Ws will come out all together. And
yeah, I think the statistics
rare. Like they've analyzed tens of billions of these collisions, and they've gotten like 270 times that they have seen this WWW, these 3 W's come out of there.
Yeah.
But the awesome thing is that number of times is not the number of times that we would have predicted based on our current understanding of particle physics.
Oh.
And that's the cool thing about it. That's the awesome thing about these particle accelerators is we can make predictions about how things will, given a certain amount of energy, what kinds of things will come out, what fraction of the time you'll get this versus that versus the other thing. And the fractions of times that we're getting this WWW is just a little bit different than what we have predicted, which opens the door to new physics. Yeah, I can't even remember now actually whether
it's bigger. It's more than was expected.
Yeah, but not by a lot. And of course, it could be. So this doesn't mean we've discovered new physics. The people who found this are not going to win the Nobel Prize just yet, because 270 is, of course, not that big a number, and it's hard to make conclusions based on that.
It depends on what it's compared to.
That's true.
The number that were expected
was 0.01, and you got 270. That would be quite meaningful. But if you expect 260 and you got 270, that probably is not. It might be a statistical. I can't remember what the number is, what they expect, but it's very possibly well within the noise. But it is intriguing because it's far enough outside. It's a few sigma outside of what you'd expect, which means it's not like the 5 sigma that you'd need in to say we found something for sure. But that means let's go.
One way of expressing it is that the number, the 270 out of 20 billion or whatever, is 8 sigma. In other words, the events are occurring with an 8 sigma significance, and they're expected to be occurring with a 5.4 sigma significance.
That's a weird way to express it. I don't know.
It is a weird way. I didn't write the paper. I didn't write this paper.
Right.
I'm not smart enough to write it, but or maybe even smart enough to read it, probably. But that's another way that they're expressing that difference.
Right. So I mean, they're seeing this thing, which they expected to see, which is cool. That means that the standard model is kind of right on, but they're seeing more of it than they should have, which means the standard model isn't quite right, maybe, unless that. So I think that there's another run of the LHC coming up, and they're just going to have to. You need more numbers, right? You need bigger number statistics in order to say whether this is real or whether it's some kind of statistical fluke. And so keep our ears posted. Maybe there's new physics in there. I mean, we have no idea what it would mean if there is. No. Well, so we've been pretty sure for decades now that the standard model of particle physics, which we've been harping on for a long, is not right, not quite right. There's something wrong. And we keep trying to find out where it is, but we haven't yet seen where it goes wrong. Maybe this is the place. I don't know. And I don't know.
You know what this makes me think, Jim? And I think this may be the answer to all this stuff. Do you remember in the original Matrix what Morpheus says to Neo? He says, "Do you ever have the feeling that there's something just not quite right about the world?" And I think that's what we're seeing here.
That's what we're seeing. You're seeing that
it's not quite right.
They got one line of code wrong, and we found it in the LHC. All right.
It's not that they got the code wrong. It's just that like the numerical rounding error when doing the calculations is starting to add up.
We're not running on a high enough precision computer, right?
That's right.
Yeah. They need an upgrade.
There are, by the way, serious thinkers that come up with that think about that kind of thing. Like, what would be the evidence that you could find that we were in a computer simulation rather than a real world? And it's
some rounding errors.
Rounding errors. Yes. I do. One of the other things I like about this is that when they're talking about like how they measure these particles, they talk about measuring their cross sections.
Yes.
Which sort of gives you the statistics and the probability, and they measure cross section to be in femtobarns.
I saw that.
Which is like
awesome unit of distance or size.
Which I love the unit barn, because you're like, oh, that's going to be a really giant thing, right? This is going to be like, and so a femtobarn, okay, it's a small giant thing. No, a barn is 10 to the minus 28 per meter squared.
Right.
It's 100 femtometers squared. It's a teeny thing.
And that the name of that unit, comes from, you couldn't hit the broad side of a barn with that. It's a cross section, but it's used in these particle physics experiments, and it's so tiny. And this is a tiny
fraction. It's a
of
little
that.
microscopic barn.
Yeah, that's awesome. Okay, well, your trivia choices. Who is in the direct family tree of Olivia Newton-John? Is it Carl Schwarzschild, he of the Schwarzschild radius, Max Born of the quantum wave density function, William Thomson, aka Kelvin, of the Kelvin temperature scale, Rosalind Franklin, whose data actually showed the structure of DNA, or James Jeans, who has named after him the gene's length. Also the gene's mass, which maybe the gene's mass will be a future sponsor of the show. What do you think? We'll start with Hannah Sargent.
Completely wild guess. Rosalind Franklin.
Okay.
Rosalind Franklin.
Jim?
I'll go with Jeans. That's how he.
Jeans.
I'm going to say that's why he got onto the Jeans thing today.
Okay.
I'm going to go with Thompson.
I stumped you all. And I really thought I wasn't going. It's Max Born, who won the Nobel Prize in Physics in 1954. And he was involved with all these Heisenberg, Fermi. He was really one of the major founding scientists of quantum physics in the first half of the 20th century. His daughter is Olivia Newton-John's mother.
Huh. Oh, wow.
Yeah. Olivia Newton-John is Max Born's granddaughter. Max Born was Jewish and fled Germany in time to England and spent the latter half of his career in England, where he met and married an English lady.
See, that's why I went for Franklin, because she's English, right?
She is English, but so is
Thompson.
Kelvin.
Yeah.
And that was my second choice, because I just thought, well, she's Australian, therefore heritage has got to be English.
Yeah, and I think Jeans is too, isn't Jeans? Anyway.
I don't know who that is.
Anyway, that was just a funny little bit of true trivia.
It was trivia.
It was very trivial. While it may have felt like the shortest day ever, it was just another episode of Walkabout the Galaxy. Give us 5 stars and we'll give you the universe. Be sure to follow us on Facebook and Instagram to get all our updates. And check out our website at walkaboutthegalaxy.com. Subscribe to our YouTube channel, Walkabout the Galaxy, which now features shorts. Catch up on old episodes wherever you get your podcasts. Follow us on Twitter.
At walk_the_galaxy.
And ask us questions anywhere using hashtag AskWTG, or just email us at wtg@ucf.edu. Our theme music was composed by Richard Drusik. Production assistance is provided by Logan Basinger. Thanks to our listeners in Iowa and around the world. Stay safe. I'm Josh Caldwell.
I'm Addie Dove.
I'm Hannah Sargent.
And I'm Jim Cooney.
We're the astroquarks, signing off until the next episode of Walkabout the Galaxy.
Bosons.